Hey everybody, what's up? This is Cameron with Danomics. So, I want to talk to you about something today that's super important but also super boring, which is log data cleanup. I want to talk to you about how we get your data interpretation ready so that way you can go through and make your interpretations with confidence that you are doing it on good data. Because as you all know, garbage in equals garbage out. So whether or not you are doing a standard interpretation or you're going to be using this data for machine learning or AI or something like that down the road, you got to get your data clean. So I'm going to talk about how we do that in Danomics. So I'm going to start off by talking about how we use flows in Danomics to do this. So flows are our batch processing system, and they are a way to run each of your well logs through the same rigorous process. So I want to go over this, and I'm just going to walk through this from top to bottom. I know it's not much to look at, but I think as I'm going through this, it'll really click for you. So we're going to start off with the log inputs. I just point this at my log database. That just tells it what I'm going to be working on. And then we move to fixed log depth problems. So I think the depth curve, it's the most basic curve. It's the one that we want to start with. And this tool does a little bit just to clean up some of the problems that we commonly see here. So issues that we see are one, the depth logs aren't sorted for some reason, or they're sorted in reverse order. The start, the stop, and the step are inconsistent with the actual depth curve itself. So we will go through and try to get that fixed up for you. Also, sometimes you'll see negative depth steps in these. So we have also have an option in here to remove negative depth steps. Um, and once you do that, that's just giving you a foundation to get started on. Then we move into this log resample. So in Danomics, it's fine if you have logs that are, 0 0.1, a half foot, 1 foot depth increments. We can handle that. But a lot of softwares can't. So, if you try to pull that into some of your other softwares, it's going to give you headaches and the software is going to crash. Well, I could say I told you so. You shouldn't use shitty software. But instead, I'm going to tell you that we can help you with that. So this log resample tool, it can either upsample or downsample logs, and it can do this at the same time. So, essentially, if you have logs that are tenth of a foot, logs that are 1 foot, we can resample those to a common reference, interpolating between those as needed. Um, and here, I'm doing this on a half foot increment. Now, once we've got that done, we're going to move into unit conversions. So units are a nightmare in LAS files for two reasons. First of all, there is no commonality for a lot of these things. You'll see stuff in decimal, you'll see stuff in percent. If you've got old logs, you'll see, your gamma ray may be in micrograms of radium per ton versus GAPI, etc. So, we're going to help you get that cleaned up. And we're also going to rename all of your units as well as converting the curves, which is important because units have as many different mnemonics as well. So, for example, just a simple percent, it may be a percent sign, it may be PCT, it may be PERC, it may be PCNT, and so on and so on. So we will go through and we have a dictionary of those we've built with our partners, but we will also use statistics to help you understand if that is the case. So, for example, if you're looking at a porosity curve that says it's in decimal, but the P50 of that curve is 5.7, that tells you that it's actually in percent instead of decimal. So we know to convert that and rename those units for you. And so that's a big win right away. Then we're going to handle some ambiguities here. So I've got this infer sGRD tool. So, if you have a curve that's called GRD, is it a gamma ray? Is it a guard resistivity? It's probably going to give you a headache one way or the other if you get those confused. So, we wrote a tool that can go in, read the units, read the descriptions, and help sort that out for you. We did something similar with the porosity here. So if you have something like an in fee or a D fee. Is that in limestone? Is that in sandstone? Is that in dolomite? Once again, we wrote tools that can go in and read the descriptions here and look for keywords like lime, limestone, LMST, sand, sandstone, 2.65, 2.71, etc. Uh, so we've got that out there for you to help you with that. We've also got, maybe a little less importantly, for resistivity, we can also go in and look for things like keywords like induction or lateral log, etc., to try to help you reclassify some of those resistivity curves in case you're trying to discriminate, hey, is this an induction log versus a lateral log? Now we're going to start to get into some stuff that's maybe a little bit more interpretive. Everything before this I consider very structural. Now we're starting to get into some more interpretive stuff. So here we have this SP baselining tool, and we can either use a rolling percentile or a low pass filter to take the drift out of your SP, make that nice and straight for you so you can understand what's shell and what's sand. We then move into what you'll see is a whole block of log math tools that I've got stacked on top of one another, and you'll see why I'm doing this here in a minute. So, for example, if I want to look at my gamma ray curve, I know that my gamma ray can't be less than 0, and if it is less than 0, it's either bad data or it's probably something that's been poorly digitized. That maybe they got maybe the null value should have been 999, and instead it's actually, or should have been minus 999.25, but instead they digitized it at minus 999, and now, like, I've got this big negative streak of gamma rays. Well, I want to clean that up. So what I'm doing here is I'm just saying, hey, if the curve is less than 0, make it null. Otherwise, leave it as the curve. Similar for resistivity. I'm doing this across all my resistivities. I'm saying, hey, if it's less than or equal to 0, which we know a resistivity curve can't be, make it null. Otherwise, leave it at 0. And we can go through and we can do this for our neutron. We can do it for our sonic. We can do it for our density, porosity, and a number of different lithologies, et cetera, et cetera. So we know how we can go through and clean this up. And so we'll do that. And after it runs through all these, then we're going to go to a tool here called null repeated log samples. So a lot of times you may have noticed you have flat spots on the top or base of your log, and this could be due to things like tool pickup. If it's at the base of the log, if it's at the top of the log, sometimes the logging engineer, they just essentially stop measuring the tool, so it just gives you the last measurement or something on there. And we give you a way to say, hey, how many samples counts as a repeat? What's the tolerance around that? And you can go through and you can clean that up. You can also do this on a curve-by-curve basis. I'm just doing it with one block here to keep life simple, but you could do this. I mean, you could have 10 of these null-repeated log samples with different tolerances and repeat bands for each of these. We then have a tool here that just removes empty logs. We have a tool here that handles curve name collisions. We can do log splicing, and this is log splicing that includes depth shifts using overlapping samples. You can also handle normalization using those overlapping samples. And then finally, we write out a new database. And I want to emphasize that we write out a new database here because we want to maintain that original data, because we may decide, oh, hey, I need to go through and I need to update this to handle some other situations that I hadn't previously seen, and we want to make sure that that writes into a new database, so that way it automatically filters through everything else. Now, most of this was fairly structural to very, very light interpretation, right? Like, yeah, baselining your SP, that's a little interpretive. Deciding where to eliminate some bad values, maybe a little interpretive, but not really. The real part of the interpretive log cleanup comes after we've ran this. We then go to our CPI. And in our CPI, we're going to bring in that cleaned up log database. And then we're going to do some additional things there. So one of the things that I see lots and lots of people doing is curve normalization. So what is curve normalization? Curve normalization is when you have a bad, you have bad or misleading data, and that's usually due to either poor digitization, it's due to the tool not being properly calibrated when it was ran on site. You get different vintages and vendors and tool types, so there can be all sorts of problems there. Also, what we see a lot is, someone's brought it into Petra, they've rescaled their gamma ray 0 to 1, they then dump that out. They don't have the original data anymore, and they got this gamma ray that's 0 to 1. And so all that needs to be cleaned up. And so, you know, in Danomics, we have a number of different ways you can do this. You can do simple shifts, which are 1-point alignments. You can do simple scales, which are 2-point alignments. You can do advanced scaling, which is 3-point alignments. We can also do spatial-based normalization, which is what I am doing here. So let me show you what I'm doing. Basically, I have this option, and I'm saying, hey, I want to, you know, assign the P5 and P95 of my well log. And what I've done is I have made a grid of my P5. I have used some tools that we have to throw out outliers based on the surrounding data. So I've got this nice cleaned up endpoint map that I then use to stretch and squeeze my data. And of course, you need to be able to QC this. So we've got built-in templates. So for example, here's my gamma ray normalization template. And I'm going to make this cross-section window a little bit bigger here. And let me reset my zoom here so we can get more well logs on the screen. And I can go through and look at how this normalization has been done. And oh, here we got one that has a pretty significant shift. And what we can see here is that the original curve shown in light gray had a very, very flat profile. Like everything was like in the 0 to 10 range. Well, now post normalization relative to its neighbors, we can see that the gamma ray is now much more similar to what we're seeing in the offset well. So that gives us some confidence that we are doing the right thing. Once again, here, slightly bigger shift, but, that puts the values that we're seeing in a very consistent range with the neighboring wells. So that's one way we can QC that. We can also come in here to the map, and we can look at things like, hey, what is, what's the amount that we shifted everything by? So here you can see this well that's on the screen now. We put a big shift on that because it was flat, or a big scale on that. But most of our stuff had pretty modest changes on it to no change at all. We can also come in and we've got pre-built things like our average gamma ray map by zone. And so you can see that, hey, we have a trend here that makes sense where we've got the Central Basin platform over here, a bunch of carbonates, lower gamma ray. Out in the basin center here, more organic shales, higher gamma ray. So, it gives you a way to go in and QC this as well. Now, I'm going to jump back here to my key well, and we're going to go back to our log view. And last thing that you will do probably is we will go through and we'll do some washout repair in here. So what we do is we give you a number of ways to define washout. You can do that by the caliper value. You can do it by caliper rugosity. You can take minimum, maximum density values, DRO values, PE and sonic cutoffs, etc. And then what you do is once you flag the washout, the software comes in here and it says, hey, here's where we flagged washouts, and it automatically repairs it using either multilinear regression or a random forest algorithm. And it goes through every combination of possible model based on your available data to give you a repair, and it helpfully removes some of these spikes that would give you misleading results in your interpretation. And once you have done that, your data is interpretation ready, and then you can go into the fun part of interpreting things like clay volumes, TOC, content, mineralogy, porosity, saturation, etc. But doing this and getting it right off the bat gives you a starting point that is going to set you up for victory going forward. All right, well, I hope that was useful. If you've got any questions, you can reach out to us at support@danomics.com if you're a customer, or if you're not yet a customer, give us a shout at sales@danomics.com, and we will be glad to hook you up with a trial. All right. Thanks, everybody.